Hi guys, we're going to talk about one variable things and how to do stats on them. So here's a column over here, and you can see, and I'll make it slightly bigger for you. You can see that there's a whole bunch of numbers. These numbers, for example, represent the birth weights of babies at a hospital. So the first 24 babies born, there's a few light babies over there, and then there's some really enormous children on the top end. So we're going to do some stats on that and see what they look like. So the first thing to do is to group the data. So in order to do that, we are going to make it into a table. So it seems like every 6 or so, or 0.6, every 0.6 kilograms seems to be a reasonable sort of category. And so we are saying that, for example, from 1.8 to 2.4, there are 5 babies, and it goes on like that. So that column over there is frequency, and that column over there is category. Now in the middle over here, we want to represent those categories by its central number. So halfway between 1.8 and 2.4 is 2.1. And if difficulty with that, count it out on your fingers. There are 7 categories, so it's category number 4, which is 2.1. So 2.1 effectively represents this 1.8 to 2.4. And in that category, there are 5. And the next thing is, what does this look like? Well, let's have a look at that, and let's draw a simple column graph, and there it is. So a column graph in the category 2.1, which we know represents 1.8 to 2.4, there are 5 babies, 1, 2, 3, 4, 5. And then in the column from 2.5 to 3.1, represented by the number 2.8, there are, how many have we got? 4 babies. Okay, so we can see a couple of things just looking at this, and if you're a visual person, you'd appreciate this. You'd appreciate that there are quite a few small babies, maybe they were premature, and then there were quite a few big babies. So you can say that, if mother says, well, about what will my baby weigh? You can say, well, depending on whether it's full term or not, we could say it's either in the 4.6 to 5.2 range, or it might be, if it's premature, somewhere between 1.8 and 3.1. So we could make those sorts of statements, knowing that they would cover a good number of the data, a good portion of the data. And there are hardly any babies in that middle range. So it seems that there are 2 categories of babies. Then the next question is, what can we do in terms of finding out representative numbers for the data? A representative number would be a number that summarizes a whole bunch of data. So we've already said that the most popular column, if you like, is the 4.6 to 5.2 column, and that is known as the modal column or category. Mode means most popular. So you'd say, the most popular weight range for a child in this hospital is 4.6 to 5.2 kilograms. Then the next set of numbers are to do with the mean, which is the average, and the median. Now we've been speaking about the columns so far, but we're going to switch back to the raw numbers in column A here. And if we look down there, we might get a different idea about what the mode is. So if we look through the numbers here, we'll say there are 2 5.1s, there are 2 4.8s, and we go down further, there are 2 1.8s. So there are 3 most popular individual weights, but if we talk about a category or a cluster, then it's the 4.6 to 5.2 over there. But looking back at the individual numbers, we can calculate what the median is. Now the median is the middle number, so if it's a small number of numbers, then it's relatively easy to see where the middle is. Now there are 24 numbers here, and so the middle number is 12. But 12 is not the middle number. 12 is the last of the first half, and 13 is the first of the second half. So in other words, it's right in the middle, is somewhere between 4 and 4.5. So you would say that the median is 4.45. And we can check that because Excel, happily enough, has a function that does this for us. And I know the obvious question, why don't we use Excel? And if you have 10 minutes, I'll tell you why. So there's 4.45 as the median. Okay, so we know we're correct. The other number is the average. Another word for the average is the mean. And so we can find out that And again, the way we would do this is add up all the numbers and then divide it by the number of numbers. So in this case, the average is 3.9. Okay, so we're going to write that down. We're going to say the mean or the average is 3.9. Now, again, we will come to y in a while, but for the time being, let's satisfy ourselves that it is the sum divided by the number. So we'll add it all up. Now, the sum here I happen to know is 93.9, and the number of numbers is 24. So I'll go back into here and put 93.9 divided by 24, and I get that number again, 3.9. Okay, so we know that's correct. And now what you'll also notice here is that the median, which is the middle point, is about the 4.5 level, whereas the mean is further up. The mean it's as though someone has moved it up somewhere up here. Now, why do you think that is? Well, because if we go back to our column graph over here, you can imagine that the median is 4.45, which is somewhere around there. Now, if you look at that bit there, it's sort of in the middle. And that's what the median is. But if you look at the mean, you would imagine this, if you were to imagine this to be a seesaw, and if you put the fulcrum over here, then you'd imagine that the weight of numbers on the left would pull the seesaw to the left. So the mean recognizes that, and it's the seesaw number that makes sure it's level. So the median doesn't care whether you've got large kids on one side and skinny kids on the other side of the seesaw, whereas the mean wants to make it exactly flat. So it recognizes that there's a lot of kids on this side of that seesaw, and so it pushes its middle back left to 3.9 away from the middle number, which is 4.45. So to summarize, if there are a bunch of kids sitting on a seesaw on both sides, the median just wants to know where the middle kid is sitting, whereas the mean wants to know if the seesaw is level.